Okay, I'm gonna go ahead and get started. Oh, my mic will work. So this is the third Sunday review session for Kima Mahapatra's CSCE 312. Today I'm going to be going over hexadecimal conversion, just because I didn't touch that when we talked about binary. And then we're going to be talking about Boolean expressions and logic gates, how they come together, which you should have been working on in lab and learning through lab. And then I'm going to talk about some of the more popular building blocks and circuits like muxes, encoders, decoders, and how they all work. Then I'm going to go over ways to store data. So it's going to be your latches, your flip-flops, your registers. And finally, I'll talk about finite state machines. So first up, I'm going to talk about hexadecimal numbers. So hexadecimal numbers are very similar to binary numbers in the sense that they're in a base. So if you have your base 2, so 2, 0, 2, 1, 2, 2, meaning this one is 2. So see how we base 0? In hexadecimal, it is base 16. So this will be the 16th to the 0th place. This will be the 16 to the 1st place, etc. for however many numbers you have. Another difference is that instead of ones and zeros, we are counting a different number of how much we're multiplying it by. So if we were to write this binary out, it would be 0 times 4 plus 1 times 2 plus 0 times 1. With the hexadecimal, we're writing it out as 2, the number here, times 16 plus d times 16 to the 0th. That d, we then look at the hexadecimal chart, we convert that d to the number that it's associated with, which is 13. A really easy way to remember this is just know that it's 0 through 9, and then every letter is just the next number. It's the reason they do this is to say if this was actually 10, you don't know it's 10, you think it's a 0 and a 1. So instead we switch to numbers. So A, B, C, D, E, F, etc. Okay, so as I said for this example, it's going to be 2 times 16 to the 1st plus D, which is 13 times 16 to the 0th, which equals 45. We have another example. So if we break this up, it's going to be, this will be times the 0th to the 1st to the 2nd. I wrote this wrong. Ignore me. This should say 2nd, not 3rd. Okay. This should be a 5. Wow, so many typos on this page. Ignore it, it's okay. So we do 5 times 16, c times 16 to the 1st, which converts to 12, and 1 times 16 to the 2nd, ends up being 453. I'm pretty sure. I can double check that right now, but it doesn't matter because we're learning. It's fine, it's fine, everything's okay. Next up, we have E and F. So this is going to be the 0th place, it's going to be the 1st. So we have E, which converts to 14, as you can see here, times 16 to the 1st, plus F, which converts to 15, times 16 to the 0th, which is 239. Okay, cool. Next up, we're going to talk a little bit, just really briefly, about how you should be working with Booleans and logic gates. So the process is expression to truth table to logic gates when you're building these things in. So here's our expression. We know that if things are touching, that means and if things are plus, that means or. This little symbol, this little apostrophe here, that's a not. So the things that we will be working with that we need to show in the truth table that we know the values to are A from AB, B from AB, C from AB not C, AB this term, AB not C this term, and not B this term. So we then just throw those in the truth table. An easy way to do truth tables is when you have multiple values and you want to make sure you're hitting all the values, is pattern them out. So you can see we have all 4 zeros and then all 4 ones. And then this one is 2, 2, 2, 2. And this one's every other. If this was only 2, it'd just look like these two here, where it's 2, 2, and then every other. Pretty simple way to make sure you're hitting, covering all your bases. Now, for this one, AB, it's going to be A and B. So it only applies when A and B. A and B and not C only applies in this case. Not B is whenever B is 0, which is every 2, 2, 2, because that's how we have it set up. And then F is when any of these things are true because these are 2 ORed. So you can see. And then to build it out in logic gates, this is with 2 input gates, just to show you all that it can be done both ways. And this is with many input gates. So we have 2 3s, but it could be however many. So with this one, we have A and B as this term right here, A and B and not C. Here's the A and B. Here's the not C that we then and with the result. Not B, which we OR with this one, and we OR with this one to make sure that all the terms are covered. And this is the same thing, but it's a lot more clear what's happening. Okay. Let me actually erase these real quick. Okay. So next up, we're going to talk about some of the more popular building blocks. This is a multiplexer, also sometimes known as a data selector, which is going to help you remember it. A mux is a device that selects between multiple input signals and forwards it to a single output. So the way it does this is it takes in this example to 4x1, 4 inputs, and uses these 2 signals to choose one of them to output. So this is kind of basically an output based on a truth table. Kind of. Yeah. So if we have, pretend this is I0, I1, I2, I3, and we have S1 and S2. These S1 and S2 are gonna be binary representations of these 4 options. So if we have S1 as 0 and S2 as 0, that means I0 is getting selected. If S0 is, there should be 0 and 1. That's my bad. I'm so sorry. Kind of a mess. Oh my gosh. Okay. Then we're going to have 0. No, we'd have 1, 0 because this is the 0th place. And that's going to select I1. Think of these as 1 or 0, 1, 2, 4. Now, if S0 is 0 and S1 is 1, we're going to be selecting this one. And if they're both 1s, we're going to be selecting this one. So it's basically what you should have done for the 7-segment display, where you know what it equates to in binary with multiple signals. Difference is this one, we are choosing which one goes to output, which is done with these gates. So as you can see, my example was if state 0 is 1. So if this is on, meaning it's going to go to these gates. And state 1 is 0, meaning it is off. So we're going to go through the not, because that'll change it. So meaning it's going to go through these gates. The only gate with two things selected is this one. So when that's I2. Actually, no, it's not. I mixed them up, but it's fine. This is a different example now. Oh, okay. So when state 1 is on, so right now we have 1, 0. So as stated earlier, this one is going to choose 2 because it represents binary 2. And this is the only gate with 2 of the 3. So now whatever the state of this, whether it's on or off, that is what is told in the output of D. Okay. Next up is just a little more about encoders and decoders. So should have used these in your lab projects. I just want to reiterate because I had a lot of questions on this. An encoder takes 2 to the n inputs and converts them into n inputs. You're going from decimal to binary. Not necessarily decimal to binary numbers. Most of the time, yes, but it's decimal to binary thinking, logic. You're reducing the amount of inputs you need to represent the same amount of things. So decoder does the opposite. It takes those few signals and makes them into more outputs. So you're going from n to 2 to the n with a decoder. Next up, we're going to talk about latches and flip-flops. I'm going to be so honest. Latches and flip-flops are probably one of the hardest thing to wrap your brain around the first time. It took me a while. It's just a different way of thinking than you're used to. So first up is an SR latch. That is what is pictured here in the top one. So it is 2 cross-connected NOR gates. And what it does is it stores that value in its output because they're constantly feeding into each other. And that's how you can store a bit of data. But the issue with these is that if set and reset are clicked at the same time, meaning set to 1 or reset to 0, the output Q has a chance to oscillate because you'll be getting inputs from both. So if this is on and this is on, then that means this should technically be going on to here, which would then make this fall, and it just gets messy. And that can happen in multiple cases, not only if like the user error processes at the same time, but if the delay is weird. So to fix this, we have level sensitive SR latches where there is a clock. Right here, the CLK means clock. And when the clock is enabled on, then that tells the system, store this value. So there's enough time given to the inputs to become stable, meaning they won't oscillate, go back and forth. And then there's this AND gate here, or these 2 AND gates here. So the clock has to be on for the value to go through. So for R or S to go through, this clock has to be yes on. So what's a clock? Because you may not know what a clock is, and that's okay. So a clock is just, in Logisim, it's a little box that has a little backwards S on it, and it's going to go off and on at regular time intervals. So the clock's period is how long it takes in between pulses. A cycle is one of those intervals, and a frequency is calculated by 1 over the period of that clock. So a D flip-flop is kind of just the upgraded version of what we had before. It's made of 2 level-sensitive SR latches that have extra design built into them to make sure that both input signals are. So it's this plus a couple more things that make sure that that oscillation isn't going to happen. 2 of those put together in a master-servant relationship design. So what this means is this piece here, the master is going to tell the servant what value it needs to be storing, and this will be storing that value. So, well, this is disabled. So if you can see here, here's the clock right here. It's denoted as a little triangle cutout. These two clocks are never going to be on at the same time because there's a NOT gate here. So when this one is off, it's going to be transferring that value to the servant because the servant is then on. Not necessarily 0, 1 on off, but like enabled. So while the master is disabled, the servant gets enabled so it can take its Q output and store it. So this fixes the problem that may occur where if you store two things within the same clock cycle, or you store two signals, you don't know how long they've really like been there or how far they've traveled because the clock is on while two different signals went in and two different signals could have gotten stored and we don't know. But this one makes it so we are absolutely sure that it only happens one value is stored per clock cycle because it's only getting input per clock once per clock cycle. So I wrote here that the data is stored when it changes from a 0 to a 1 at the rising edge. So if we think of a clock, it is basically this, where this is when the clock is off, so at 0, and this is when the clock is on at 1. That value gets stored right here as soon as it flips. Okay. So next we're going to talk about registers, because registers are just groupings of multiple flip-flops that share a clock signal. So you can see in this diagram here, here's its one clock. It gets fed into all of them. And now it can store 4 bits. Remember that these are entire flip-flop cells. So this, each one of these is a whole one of this, not just two latches, not just like a latch. Each one of these is an entire flip-flop made of 2 latches. So you can store with 4 of these flip-flops together, 4 bits of data that you can then keep together. So when I talked about register a couple of weeks ago as part of a computer, that's what a register is. It's something that stores data. So I'll bring back this diagram with these labeled. Okay. Last up, I'm going to talk about finite state machines. So FSMs are used to keep track of / describe the behavior of a sequential circuit. So if you're doing multiple things in succession, you're storing multiple bits of data, you have an output, you want to know what it's going to be while you're working on that clock cycle, or depending on what cycle you're in, what you're doing, that is what we use an FSM for. They're easy to draw diagrams for, and from those diagrams, it makes it a lot easier for you to actually build them and understand what they're doing. So every time we see a diagram like this, we can assume that the transition is occurring on the rising edge of the clock. So you don't really need this CL here, because we're assuming that it's the rising edge, just for the purpose of this class, because otherwise things get confusing and it's a lot more complicated than need be. Cool. So they can be drawn. This is what a state diagram is with a state diagram. Or if you want to describe them in words, you have to tell what the set of state is. And by set, I mean like CSCE 222, like curly bracket set. So you describe its set of states, its set of inputs, its set of outputs, its initial state, the set of transitions, and the set of actions. And you can implement an FSM as a sequential circuit, which is also known as a controller. So real quick, I'm just going to talk about this. So this is a clock cycle diagram. State can be off or on, or if you want it to output 2 when it hits here and 13 when it hits here, you can change these to say 2, 13, 2, 13. And if there are registers that are storing those data and you put them out, like that's this stretched hexagon shape is the state. So here's the clock cycle where the clock is off and on. And this just describes the behavior. So up on top. So if we have, say this is the clock. I know it's not, but it's easier to say this is the clock right now. If it is on the bottom line of the diagram, that means 0, off. This is the rising edge. If it's at the top, that means 1, on, falling edge, etc. Okay. And then to create a controller, what you want to do first is create the FSM that describes the behavior you are wanting the controller to have. So you create this bit here, the picture that helps you understand. You then use a state register and combinational logic. So you set it up like this. The register, that's going to be a register. Those exist in Logsim or whatever you're using. Or you can make them with what we just talked about here. And then the combinational logic, which won't be done yet, but you'll be able to set them up and put them together. Then you encode each state. Each one of these is a state by giving it a unique binary number. So this one is 0, 0, 0, 1, 1, 0, 1, 1, also known as off, on 1, on 3. You then create a truth table with each state and the inputs and the outputs so that you can know what the output will be of each state when it is currently happening, as well as what your next state will be based on the inputs. Then, based on that truth table, you can get the equations, condense them down, and implement that combinational logic within your controller. So that's a lot to think about, but overall what you're doing is you're deciding what you want each state to do when a certain input is put in, and then you're putting those logic gates together so that what you want to happen when that state is on and what the input that you want is happening happens. So here's an example that I drew up. So in this example, I have 3 states. I put another circle around this one because this one is the starting state. My input is A. C0 is what I named my state, and the output is X. So if we look at these, S1, S0. S1, S0. S1, S0. Okay. So the way I set this up, this is the starting state. While A is off, A is 0, it's going to keep looping back through this state. If A turns on, the next cycle, it will be moving to here. That was really important, what I just said. If A is on, the next cycle, it will be moving to here. For my C1 state, output is 0 once again. If A is off, A is 0, on the next cycle, it will be moving back to C0. If A is still on the next cycle, it will be moving to C2. This is my third state, C2. This one, the output is 1, on. If the input is still on the next cycle, it will continue to loop in this state C2, stay here. If it is off in the next cycle, it will move back to C0. Okay, so how did I make this truth table? Okay, we're at C0. At C0, my S1 and my S0 at C0 are 0, 0, because that is what C0 is. This is the current state you're at. So these are current. We'll get to these. So those 2 numbers correspond with my S1 and S0 of my current state. So this whole box is going to be 0, 0, because that's what C0 is. Now, we're going to test each type of input. So this, a 0 would be A naught. This would be A. Same thing all the way down. You're going to test each type of input. So if I am at state 0, 0, and my input is 0, I know that my output will be 0 because I'm at state 0, my 0th state. So I know my output is 0, and I know that my next state will also be 0, 0 because we're staying here. So these two correspond with the next state. So this could be n1, n0. Okay, if I am at C0 and A is on, I know that the next state I will be moving to is 0, 1, but my output is still 0. For C1, when I'm at state 0, 1, which is what this whole thing will be because we're at 0, 1, and if the output is 0, I will be moving to 0, 0 next time, but I know my output right now is still 0. So at 0, 1, if A is on, A is 1. I'm still at 0 because I'm still in C1, but I know that my next stage will be 1, 0. Then, when we're at stage 1, 0, if output is off, I'm at C2, I'm at 1, 0, so my output is going to be 1 because I'm currently at C2, which has an output of 1. But I know that my next stage, I will be going back to 0, 0. If I am at 1, 0, C2, and my output is 1, A, I know I'm staying here. My output is 1 because I'm at the stage where output is 1, but I'll be staying at 1, 0. And that is basically how a finite state machine table is done. It takes a couple tries to really get comfortable, really understand it, but after you do that, you can use these lines to make your Boolean expressions and then set up your combinational logic. Alrighty, so that is everything I had prepped for today. I can take questions now.